Hello, today we're going to go on to section 13.3, which deals with the dot product. All right, so with further ado, what is the dot product? We look down here. I'm going to define the dot product for a three-dimensional vector, but we also could define it for a two-dimensional vector also. If you look, if we have here, if vector A is equal to A1, A2, A3, and vector B is equal to B1, B2, B3, then we define the dot product of A and B to be A dot B, and it's a solid dot, it's not multiplication. A dot B is equal to A1, B1 plus A2, B2 plus A3, B3. Now, if your vector is just two-dimensional and you don't have this A3, B3 piece, you'll just have an X and a Y coordinate, then your dot product won't have this piece right here. It'll just be multiply your X coordinates together plus multiply your Y coordinates together and then take the sum of those. Now at this point, I'm sure you're thinking, why would anybody do this? Why would you want to do this? What is it going to give me? We're going to find that out today. All right, but first of all, we have to learn how do you do the dot product. Now notice when you take the dot product of two vectors, this is two vectors and we're taking the dot product, our answer is a number. We get a real number. So this is mapping an operation between two vectors to give you a number, which is going to tell you some very important and useful information. So first of all, let's practice. How am I going to take the dot product of the vector 3, 2 with the vector 6, 1? And all we do is multiply together your x coordinates. So we're going to take 3 times 6 plus 2 times 1, and I don't like that pen. Let me use one a little bit bolder. And so I get, what do I get here? I get 18 plus 2, which is equal to 20. So the dot product of these two vectors is the number 20. Your answer with a dot product is a scalar. It's a number, a real number. If I wanted to take the dot product of these two three-dimensional vectors, all I do is I take 1 times 4 plus 2 times 1 plus a negative 3 times a 2. That's all I do. And that's going to give me, let's see, 1 times 4 is 4, 2 times 1 is 2, negative 3 times 2 is a negative 6, and this gives me 0. And we'll find out later today when the dot product of two vectors gives you 0, it's going to give you some very useful information. In fact, we'll find out later that that's going to tell us that these two vectors are perpendicular. They form a right angle. Okay, but we don't know that yet. All right, and now, if they give me my vectors in terms of I, j, and k, it might be helpful for you first to change this to writing it in component form. This is 3, 2, 4, dotted with 3. Now notice it doesn't have a j there. So the j component is 0, comma, negative 1. All right, and therefore, if I take 3 times 3, I get 9, plus 2 times 0, I get 0, plus the product of the z coordinates is 4 times a negative 2 is a negative 4, and so that dot product is 5. Okay, so now we know how to do a dot product, but we really don't know why you would want to. But first you have to know how to do it. All right. Recall. I'm going to give you some reasons why we care about what a dot product is. What can it do for us? Recall, when we learned how to do, we first learned about vectors, we learned one very important thing. If we wanted to find the magnitude or the length of vector A, what we did is we took the square root of A1 squared plus A2 squared plus A3 squared. And remember, that came from the distance formula, because in reality, what we did here was, all right, if you drew your vector emanating from the origin, here's the origin 0, 0, 0. And if I had a vector with components A1, A2, A3, if I plotted the point A1, A2, A3, maybe it's up here, this vector represents this vector with components A1, A2, A3. And if you use the distance formula to find the distance between these 2 points, you would get exactly this. All right, so remember that the magnitude of a vector is the square root of the sum of the squares of its x, y, and z components. Well, note now, since recalling that this gives us the length of our vector, if I have vector A is A1, A2, A3, all right, if I take A dot A, I'm taking A1, comma, A2, comma, A3, and I'm dotting it with the vector A1, comma, A2, comma, A3. And what do I get here? I take this x component times that x component, which gives me A1 squared, plus a2 times a2 is a2 squared, plus a3 times a3 is a3 squared. And remember, the magnitude of a was given by the square root of a1 squared plus a2 squared plus a3 squared. And so this looks just like the magnitude, but I'd need to take the square root of it. Take the square root of this and the square root of this. So in other words, a dot a is giving you the magnitude of a, the length of vector a, squared. Or if you wanted to find the length of vector a, you would take the square root of the vector dotted with itself, which is very helpful. Okay, so this is one thing a dot product is good for. If you take a vector and you dot it with itself, you're getting the length of the vector squared. So that's one thing that a dot product is good for. And there's much more though. All right, moving along. If we went through, and we're not going to, we could actually prove all of these properties that I have right here. The first one, notice, is a dot a is the magnitude of a squared. And these properties, by the way, are listed in your book in section 13.3, so you don't have to frantically copy them down because they are in your textbook. Notice a dot b is equal to b dot a, and of course that makes sense because remember, if vector a is like a1, a2, a3, and vector b is b1, b2, b3, right? If I take their dot product, what do I get? If I take their dot product, I'm going to get a1, b1 plus a2, b2 plus a3, b3, and duh, I think a1 times b1 is the same as b1 times a1, right? And a2 times b2, this is the same as b1 times a1 plus b2 times a2 plus b3 times a3. And what would that represent? That would represent the vector b1, comma b2, comma b3, dotted with a1, comma a2, comma a3. And we've just proven that the dot product is a commutative operation. We could do that for all of these other properties, but I'm choosing not to because I don't want to put you to sleep today. All right, but it's nice to note that we have a distributive property for dot products, and you could do the exact same thing. Write vector A is A1, B1, A1, A2, B2, and write B is B1, B2, B3, and write vector C is C1, C2, C3, and actually do it out, and you can justify to yourself that these are true. So we have a distributive property. A dotted with the sum of vectors B and C is equal to A dot B plus A dot C. We also have, now notice C here doesn't have a cap on it. Do you see that? That means C is a scalar, like it's the number 2 or the number 3 or the number square root of 3 over 5. All right, it's a number. So if you have a plain number times vector A and you're dotting it with vector B, if we wanted to write all this out, we could. We could prove that it's the same as taking A dot B and then multiplying it by C. Or if you wanted to, you could multiply C times B and then dot it with A. In other words, scalar, the dot product sort of has properties just like regular multiplication did with real numbers, if you notice. It acts very much like real numbers, but you're taking a dot product of two vectors to produce a number, a scalar. Also, the 0 vector dotted with A is going to give you the number 0. Well, duh, of course, because if you dot 0, 0, 0 with A1, A2, A3, you're going to get 0 times A1, which is 0, plus 0 times A2, which is 0, plus 0 times A3, which is 0, whoops, plus, which is going to give you one big 0. All right, we have a few more properties I'd like to go over. Oh no, I think that's it. Yep, I apologize. So we just have those 5 properties. Now, I want to go back to your Trig 2 days. And by the way, people, you don't have to be frantically copying this down. All right, I just want to prove something to you, and I want to justify why it is true. All right, but don't think you've got, I'm not going to test you on what we're doing right now. But if you recall, back in your Trig 2 days, if you had a triangle, and you had the length of 2 of the sides, if I have the length of B and the length of A, and I have the angle, the included angle between them. You might remember from those of you that took Trig 2 here at Del Tech, I know MAT 182, you actually did cover this, so we should remember it 2 semesters ago. We had what was called the law of cosines, which said that the side opposite the angle that you knew, c squared, was equal to a squared plus b squared minus 2ab cosine theta. Okay? If I had asked you, what is the law of cosines, you might go, oh, I remember having it, but I don't remember it exactly. But now you go, oh, yeah. So in other words, notice if you had a right triangle with sides A and B, and the included angle is 90 degrees, and this was side C that I wanted to find, notice cosine of 90 is 0. This part drops out and you get the old Pythagorean theorem. Okay, but you remember this? Yeah. Okay, so that's the law of cosines. Now what does that have to do with dot product? I want you just to follow along. Look at this picture I have in 3D. First of all, I want you to notice if I drew vector B here and vector A here, this vector that starts where B's arrow ends and ends where A arrows ends is actually vector A minus B. Do we all see that? Because notice, if you drew B, here's B, and if I drew A minus B, where B ends, notice this is the resultant of the sum of those two, and notice if I write out B plus A minus B, I think most of you will notice this gives me B plus A minus B. The B's cancel, and I get vector A, which is indeed the resultant, the vector that starts where the first one starts and ends where the second one ends. So this vector right here is A minus B. Okay? Now, what does that have to do with the law of cosines? Well, suppose, let's just suppose, okay, let me write this out a little bit. Let's say we know vector A, we know vector B, and we know the angle in between them is theta. All right? Let's figure out what is A minus B dotted with A minus B. What does that give me? We just said, remember a few minutes ago, we said if you take a vector and you dot it with yourself, you get the length of that vector squared. Remember that? We proved that. A vector dotted with itself gives us the length of that vector squared. Now to make life a little bit easier for myself so I don't have to write so much, let's use a little bit of shorthand here. I'm going to say the length of vector A is just little a. Okay? The length of vector B is little b. And I'm going to say the length of vector A minus B is, I'm going to call it C. So this triangle right here has sides A, B, and C. All right, well, do we all see? If I take A minus B and dot it with A minus B, this gives me C squared. All right? It gives me the length of this side right here. But now the law of cosines tells me that the side opposite the angle, A minus B, dotted with A minus B, is equal to the length of this side squared. Let's go back and look what it says. This side squared plus this side squared minus 2 times this side times that side times the cosine of the included angle. So the law of cosines with this triangle right here says to me this is equal to A squared plus B squared minus 2AB, the cosine of the angle between them. All right? But now I'm going to take this side, and I told you don't have to copy this down. I just want you to follow. I'm going to take this and use those rules of all of these things that we said we could use. All right? So this acts just like A minus B times A minus B. So if I want to multiply that out, it would be A dotted with A. Now, A dotted with minus B would be minus A dot B. Minus B times A is minus B dot A. And minus B times minus B is plus B dotted with B. And we have this equal to A squared plus B squared minus 2AB cosine theta. And right now you're thinking, what is this woman doing? But just watch. It's going to be pretty cool. Now watch. What does A dot A give you? A squared. Now remember, we proved, in fact, that A dot B and B dot A were one and the same, right? So here I have minus A dot B minus B dot A. So since B dot A is the same as A dot B, it'd be the same as minus 2A dot B. You all with me? I'm combining these two together. And then I have B dot B, which is what? B squared. And on the right-hand side with the law of cosines, I have A squared plus B squared minus 2AB cosine theta. Well, my goodness, look what happens here. We have an a squared on the left, we have a squared on the right. I think we can cross them out. We have a b squared on the left, we got a b squared on the right. We can cross that out. So I have minus 2 times a dot b is equal to, minus 2 ab cosine theta. Well, since we have a negative 2 times and a negative 2 times, is it okay if I divide through by negative 2? And look what I have. A dot b is equal to a times b times the cosine of theta. This is big time important stuff, guys. This you want to write down. What we have just proved is, if you do that wacky little dot product, multiplying the x coordinates together, the y coordinates together, the z coordinates together, and then adding them up, it gives you the length of each of the vectors multiplied together times the cosine of the angle between them. Big important stuff. This is why we do the dot product. This is why we use it. This is going to give us a lot of information in a few minutes. All right, so notice what we did. We said if you have vector A and you have vector B and you take theta, what the heck is theta? Theta is the angle between them. We have just proven that A dot B is equal to the length of A, which I wrote as little a, times the length of B times the cosine of the angle between them. So now you have two different ways to do dot products. If you have vector A equal to vector A1, A2, A3, and you have vector B equal to B1, B2, B3, and I want to take A dot B, I now have two ways to do it. One way is to take the length of A times the length of B times the cosine of the angle between them. And yes, 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 we can also take A1 times B1 plus A2 times B2 plus A3 times B3. You have two ways to do the dot product now. Two. And sometimes you're going to use the one formula, and other times you're going to use the other formula, or sometimes you're going to do it both ways and set them equal to each other. Okay? Important. You put a star by that. If you've been sleeping through my lecture, this part you want to make sure you have down on your notes. Okay, we doing all right? Okay. Now, look at this though. Let's look at this. A dot B is equal to the length of A times the length of B times the cosine of the angle between them. What if my one vector looks like this and my other vector looks like this, and the angle between them is 90 degrees. Then I have A dot B is equal to the length of A times the length of B times the cosine of 90 degrees. So I recall the cosine graph looks something like that, and at pi over 2 or at 90 degrees, cosine of 90 was 0. So if two vectors are perpendicular, their dot product will equal 0. Vice versa, if you have two vectors and the vectors are not the 0 vector, if the dot product turns out to be 0, since this isn't 0 and that's not 0, that's got to be 0. So the angle between them could be 90, and you could say, oh yeah, maybe it's 270, Mrs. Strocko. Cosine of 270 is also 0. Well then, big whoop, the one vector looks like this and the other vector will look like that. And you can either measure it that way or you can measure it that way. I don't really care. So what do we have here? If A is perpendicular to B, then the angle between them is 90. A dot B is the length of A times the length of B times the cosine of 90. But since the cosine of 90 is a big fat 0, we get 0. So if two vectors are perpendicular, their dot product will be 0. A lot of times, guys, if you want to know if your vectors are perpendicular, what you're going to do real quick is you're going to take the dot product. And if you've got 0 there, you say, life is good. I've got myself two perpendicular vectors. In summary, I have A is perpendicular to B if and only if A dot B is equal to 0. Okay. Just check something here. Yeah, we're fine. Moving along. Next thing I want to do, I see one thing I want to figure out. Oh, I want to show you something else though before I go on to this. Notice, this is something you're going to use a lot. Notice, since A dot B is the length of A times the length of B times the cosine of the angle between them, notice you could divide by the length of A and the length of B and get the cosine of the angle between your vectors is A dot B divided by the length of A times the length of B. You follow? So if you know A, you know B, you know its lengths, you can find the cosine of the angle. And if you use the inverse cosine, you can actually find out what that angle is. Okay, and we'll be doing some like that. Okay, what do I mean by projection of B onto A? Now remember, two vectors, you can always slip and slide your vector any way you want, because what determines a vector is its length and its direction. So this vector and the one that's exactly parallel to it in the same direction is the exact same vector. But what do I mean by the projection of B onto A? If I extend the line that goes through A, draw the line that goes through vector A. If I want to do the projection of B onto A, all you do is drop a perpendicular from the tip. First of all, you draw your vector's tail to tail, and then you draw a perpendicular to the line that goes through A. This length right here, that is the projection of B onto A. Okay, that's the projection of B onto A. Now, I'd like to come up with a formula for how long is that? Okay, how long is that? How long is the projection of B onto A? First of all, I want to look at a right triangle, just review just a little bit of baby trig. If you have a right triangle, okay, right triangle, and you know this angle, and let's call this the hypotenuse. Suppose I want to represent the length of this side. I'll call that x. How can I represent the length of this side? Well, last time I looked, the adjacent side over the hypotenuse is equal to what? What's adjacent over hypotenuse? Cosine. And in other words, x, the length of this side, is equal to my hypotenuse times the cosine of the angle, right? So this length right here is my hypotenuse times the cosine of the angle. In fact, if you have, we also could call this little side y here if you want to, y. Notice y over h is equal to what? Sine of the angle. And so if I multiply through by h, y is equal to the hypotenuse times the sine of the angle. So a little thing that's sort of neat to remember is if you have a right triangle here, and here's theta, okay, and here's your hypotenuse, the side opposite the angle is the hypotenuse times the sine of the angle, and the side adjacent to the angle is the hypotenuse times the cosine of the angle. The way I remember that is I just remember this dopey little thing called SOS. It means sine goes with the opposite side. Sine goes with the opposite side. Then cosine's by default the other one. Okay, now what does that have to do with this? Okay, well, let's look at this. The length of this side right here is the length of vector B. This, let's ignore this little a right here. We don't even worry about him. If I knew this angle here, my hypotenuse is B. So since this is the adjacent side, the length of this side right here, that projection of B onto A, would be the length of B times what? The sine is the opposite side, so the cosine is the adjacent side. So the length of this red, the projection of B onto A, I could write it as the length of B times the cosine of A. You with me? So the projection of B onto A is equal to the length of B times the cosine of the angle between them. Now, as I'm the teacher, I can do whatever I want. I'm going to take this, and I'm going to multiply it by a form of 1. I'm going to multiply top and bottom by the length of A. You all with me? So the projection of B onto A is the length of B times the cosine of the angle between them. Does everybody see I just multiplied by the length of A over the length of A? It's a form of 1, it really cancels. Except people, what does that numerator equal to? What's the length of A times the length of B times the dot product? Isn't that cool? So we've just figured out, we have a formula. If we want to take a vector. We have vector B here, and we have vector A here. And we draw the line that goes through vector A. And we draw a perpendicular from the tip of B down to A. That's the projection of B onto A. That's this line segment right here. And if I want to figure out how long is that, the projection of B onto A, it would be, notice it's the projection of B onto A. You take the dot product of A and B, and you divide by the length of the one that you're going on to. Okay, so let's put that down. We call it scalar projection of B onto A, and we just proved that your book writes it like this way. They're saying the component of B onto A, and all that is here's vector B, here's vector A, and the component of B onto A would be, if you extend this line, drop a perpendicular down, it's the length of this line segment for where B starts to where that perpendicular ends. The length of that line segment is A dot B divided by the length of A. Now the good news is, remember when you take your test I said you can bring a cheat sheet? You should not be making the cheat sheet up the night before the test. You should be making that cheat sheet up with each section that we're working on and saying, oh, dot product, I think I want to write that down. Ooh, this projection, I think I want to write that one down. Now they call this scalar projection because this is giving you a number, how long that line segment is. You with me? It's giving you a number, how long that line segment is. Now, what if instead I don't want to write it as a scalar? I don't want to just have the length of that line segment, but I want to represent this vector. This vector that goes from here to here. I already know how long that vector is, don't I? That vector's this long. That's how long that vector is. So now, how can I represent a vector that's this long and going in the same direction as A? Well, remember, when you multiply a vector, like if I take one vector, a vector V. If I take a vector V and I multiply it by 2, I'm getting a vector that's in the same direction as V, but twice the length, right? If I multiplied it by 12, I'd be getting a vector that's the same direction, but 12 times the length. What if I have a vector V and I want to get another vector that's of length 1? How can I do that? Remember, you would divide it by its length. If I take vector V and divide it by its length, I'm getting a vector that's the same direction as V, but its length is equal to 1, right? Because like if vector V was of length 2, if you divided it by 2, now your length would be 2 divided by 2, which is 1. If vector V was maybe of length 10, you're dividing it by 10. Oh yeah, it's a tenth the length. Its length is going to be 1. So how can I represent a vector that's in the same direction as A? I want a vector. Same direction as A, but I want it to be of length 1. How can I get a vector that's the same direction of A, but of length 1? Oh, take A and divide it by its length. This vector goes in the same direction as A, but it's of length 1. But I want a vector that's in the same direction as A, but it's this long. Well, if this vector is of length 1, if I multiply it by 2, I have a vector that's of length 2, don't I? Because 2 times 1 is, what if I multiply that vector by 3? I have a vector whose length is 3, right? If you take a unit vector and you multiply it by a number, you're getting a vector in that direction, but of the length of the number you're multiplying it by. So if I want to have a vector that's the same direction as A, the same direction as this unit vector I just came up with, but of this length, what can I multiply by? That number. Now, notice, this is a number, this is a number, this is a number. What's this? A vector. So I'm going to write this as A dot B over length of A times length of A times A. All right, and we could rewrite that as A dot B over length of A squared times A. And what is this? This is giving me a vector that's the same direction as A, but it's the same length as the projection of B onto A. Now what I remember to do is, whenever you want to get a length of vector of length 2, but the same direction as your vector, first divide it by its length, that makes it a unit vector, and then multiply it by the length you want to have. And here's the summary. the projection of B onto A, if you want to, the vector projection of B onto A, we just proved this. You can write it as A dot B over the length of A squared times A. Do I memorize this formula? Nah. It's too much to memorize. Okay? All right. A couple more definitions, and then we're going to go over some exercises quickly. Direction angles. What the heck is a direction angle? Well, let me show you. Here's a vector A, and it's in three-dimensional space. This is the x-axis, the y-axis, and the z-axis. In three-dimensional space, we have what's called the direction angles, and they have names, Greek letters, alpha, beta, and gamma. That one's gamma. If you're writing it freehand, you just go like that. That's gamma. Okay, it looks like a little ribbon. Okay? Now, angle alpha is the angle that your vector makes with the x-axis. So if you slid your vector so that it's starting at the origin, and you measure what angle does this vector make with the x-axis, that's angle alpha. If you take what measure A makes with the y-axis, that's beta. And what angle does A make with the z-axis? That's called gamma. So alpha, beta, and gamma are the angles that your vector makes with the x, y, and z axes, respectively. Not hard. Now, close this first so you can't see it. Here is vector A. And again, don't take this down. Just sit back and follow it instead of frantically copying my notes. By the way, remember I have all this on the Blackboard thing. So if you go to blackboard.dtcc.edu and you click on course documents and click on visuals, you can get these notes back. But now, let's look. Here's vector A. All right. Now, what was alpha? Alpha was the angle that A made with the x-axis. So this angle right here is my alpha. And remember what little I with a cap on it is. What's I? I is the unit vector that goes in the same direction as the x-axis, but it's of length 1. All right? Now notice, if I take A, we're assuming that I don't like that pen for us. We're assuming that A is the vector has components A1, A2, A3, right? That's what our A is. Let me move this a little down so you can see it, depending on what your TV is, all right? Now notice, let's look here. What if I take A dot I? A is A1, A2, A3, and I, remember, has components 1, 0, 0, because it's 1 in the x direction and 0 in the y and z direction. So if I take A dot I just get A1, because A1 times 1 is A1, but A2 times 0 and A3 times 0 are zeros. Now we could also use our other definition for dot product. A dot I is the length of A times the length of I times the cosine of the angle between them, but the cosine of the angle between them is alpha, because alpha is defined as the angle between your vector and the x-axis, and I is going in the direction of the x-axis. What's the length of I? 1. So we have the length of A times 1 times the cosine of alpha, which is this. All right? Now, since A dot I is equal to A1, and A dot I is equal to the length of A times the cosine of alpha, we could set this and this equal to each other because they're both equal to A dot I. All right, and we have A1 is equal to the length of A times the cosine of alpha. So if I divide by the length of A on both sides, I'd get the cosine of alpha is equal to A1 divided by its length. You all with me? This is called the direction, one of the direction cosines of your vector. All right. What do you think the cosine of beta would turn out to be? The cosine of the angle that your vector makes with the y-axis. What do you think that would be if I went through it? Because alpha, beta, and gamma are the angles that your vector is making with the x, y, and z axes respectively. We have vector A was equal to A1, A2, and A3. We just proved the cosine of the angle that this vector made with the x-axis was the x-coordinate divided by its length. What do you think cosine beta is going to be? I bet you it's the y-coordinate divided by its length. What do you think cosine gamma is going to be? I bet you it's the z-coordinate divided by its length. And these are called the direction cosines of vector A. Okay? Right now you think, why? Who cares? But you'll see. These things are going to come back into shape later. Okay, so I have it written here much nicer. If vector A is A1, A2, A3, and it makes angles alpha, beta, and gamma with, this shouldn't say with A, with, it should say the X, Y, and Z axes respectively is what it should say, then the direction cosines of A are given as cosine alpha is A1 over the length of A, cosine beta is A2 over the length of A, and cosine gamma is A3 over the length of A. All right, let's do a couple problems. First one I want to look at is exercise 10 on page 848. It says if the length of A, find A dot B given the length of A is 4, the length of B is 10, and the angle between vector A and vector B is 120. Now remember, we have two ways to do dot products, don't we? Let's go back and look what the two ways are. One way is if A is A1, A2, A3, and if B is B1, B2, B3, right? A dot B was A1 times B1, that's a 1 there, plus A2 times B2, plus A3 times B3. We also have A dot B is the length of A times the length of B times the cosine of the angle between them. Now we have to decide which one we should do. Well, in this particular one, they gave me the length of A, they gave me the length of B, and they gave me the angle between them is 120 degrees. So I think I want to use that A dot B is the length of A times the length of B times the cosine of 120 degrees. Length of A was 4, length of B was 10. I have to figure out cosine of 120 degrees yet. You could pop it into your calculator if you wanted to. I prefer not to. All right, I prefer, let's draw 120. Where's 120 degrees? Remember, cosine of an angle is your x-coordinate over your hypotenuse, right? Where's 120? What quadrant? 3. About here's 120. So what's this little baby angle right here? 60. And I remember, if you have a 30, 60, 90 triangle, one triangle that has 30, 60, 90 has sides what? Can you give me one triangle whose angles are 30, 60, and 90? 1, 2, square root of 3, right? It goes like 1, 2, buckle my shoe. 1 is the smallest of those three numbers, so it would be opposite the 30. 2 is the largest, so it would be opposite the 90. And root 3 would be opposite the 60. So coming back here, I'm going to draw a little triangle right here, a little right triangle. Ah, that's 60, this is 30. So the side opposite the 30 is 1, the hypotenuse is 2, and this side is square root of 3. Now notice, x is a negative 1, because when you plot this point here, you go back 1, up 1. Y is square root of 3. So the cosine of cosine of 120 is x over r. The x-coordinate is a negative 1, and r is 2. You know, if you popped in your calculator cosine 120, I think it would tell you negative 0.5, and you'd be able to figure that out. But this is a negative 1/2, and 4 times 10 is 40 times a minus 1/2 is minus 20. So the dot product of those two vectors is a minus 20. Okay, moving right along. Let's look at exercise 13 on page 848. They say show that I dot j, j dot k, and k dot I are all equal to 0. I'm not going to do all three. I'm just going to point you in the right direction. Remember, when you take I dot j, it's equal to the length of I times the length of j times the cosine of the angle between them. Now let's just draw this for a second. Remember, I is the unit vector in the x direction, and j is the unit vector in the y direction, and z, or k, excuse me, is the unit vector in the z direction. So what kind of angle do all three of those make with each other? 90 degrees, right? Like if you do it in 3D, maybe i's pointing that way, j's pointing that way, right? And k is pointing perpendicular up. So all three of them make a 90-degree angle with each other. They're all perpendicular to each other. Do you see that? You can think of x-axis going this way, y-axis going this way, z-axis going this way. This is a 90 degree, this is a 90 degree, and This is a 90 degree. So if they're all 90 degrees, since cosine of 90 is 0, we will get 0. Now another way you could have done it is you could say I is the vector 1, 0, 0, and j is the vector 0, 1, 0. And yeah, if I take I dot j, I'm going to get 1 times 0, which is 0, plus 0 times 1, which is 0, plus 0 times 0, which is 0. Okay. All right, let's go on and do the next one. Show that I dot I, j dot j, and k dot k is equal to 1. We're just going to do I dot I. All right, and let's look at this one. If I have I dot I, it's the length of I times the length of I times the cosine of the angle between them. Well, what's the angle between I and I? I is pointing in this direction. Okay? Well, what's the angle between a vector and itself? 0. And what's the cosine of 0? 1. Length of I is 1. Length of I is 1. Cosine of 0 is 1. We have 1 times 1 times 1 is 1. That's one way you can do it. Another way you can do it is you can say I is 1, 0, 0. And so if I dot I with itself, I dot I is 1 times 1, which is 1, plus 0 times 0, plus 0 times 0, and I get 1. Okay. All right, next one. Find the, aha, I love this one. Put a star on this one. It's going to be on your test for sure. All right? It says, find the angle between the vectors. First find an exact expression, and then approximate to the nearest degree. Okay, find the angle between the vectors. First find an exact expression, and then approximate it to the nearest degree. Now notice, vector A, if I write it in terms of components, is 2, negative 1, 1. And vector B is 3, 2, negative 1. All right, now remember, A dot B is equal to the length of A times the length of B times the cosine of the angle between them. So the cosine of the angle between them, if I divide by the length of A and the length of B, is going to be A dot B divided by the length of A times the length of B. Okay. All right. Okay. So what we can do here, all right, is to find the cosine of the angle between them. The cosine of the angle between them is, let's see what we got here. Let's first figure out what is A dot B. Let's do this over here first. A dot B is equal to, let's see, 2 times 3 is 6, plus negative 1 times 2 is negative 2, plus 1 times negative 1 is negative 1, and that gives me 6 minus 3 is 3. Okay, so A dot B is 3. Okay, now we also have to figure out what's the length of A. Well, let's do that next. The length of A is the square root of 2 squared, which is 4, plus a negative 1 squared, which is 1, plus 1 squared, which is 1, gives me square root of 6. Remember, I'm using the formula. If you look, if A is A1, A2, A3, I'm using the formula that the length of A is the square root of its x component squared plus its y component squared plus its z component squared. So the length of B is going to be the square root of, now what's B? B is 3, 2, negative 1. So 3 squared is 9, 2 squared is 4, negative 1 squared is 1, so that gives me square root of 14. So the length of A is radical 6, length of B is square root of 14, and A dot B was 3. So plugging that in, we figured out that A dot B was 3, length of A was square root of 6, length of B was square root of 14, so I have the cosine of theta is 3 divided by the square root of, what's 6 times 14? 14 times 6, 84. Now we could, if we wanted to, say square root of 84 is square root of 4 times square root of 21. So it's 2 square root of 21. And your book will do that 1 T1. So theta, how do I write theta is the angle whose cosine is? That's the inverse cosine. Inverse cosine of 3 over 2 square root of 21. Okay, and I notice my calculator's not hooked up, so I can't turn it on. But people, if you take out your calculator and you put it in degree mode, which you know how to do, and then you go inverse cosine, and you actually put in, heck, you could put in 3 over square root of 84. You don't have to do this 3 over 2 square root of 21. It will miraculously give you, because I already did it ahead, it will give you 70.9 degrees. Isn't that cool? So we can find the angle between two vectors by using this lovely formula here. Do I memorize this formula? Do I memorize this? No. I memorize this one. I memorize A dot B is length of A times length of B times cosine of theta. Divide by length of A, length of B, you got the cosine of the angle. And if you use inverse cosine on your calculator, you got that angle in 2 seconds. Nice problem. Okay, determine whether the given vectors are orthogonal. What does the word orthogonal mean? I didn't give that to you yet, did I? What does orthogonal mean? What do you think it means? Perpendicular. Orthogonal is another word for perpendicular. So they want us to determine whether or not these vectors are perpendicular, parallel, or neither. Now, how can we check to see if they're orthogonal or perpendicular to each other? How can we check that? How can we check that? How would you check to see, are those vectors perpendicular? How could I check that? Dot product. Try the dot product. Remember, if the dot product of two vectors is 0, they're perpendicular. So let's try u dot v. U dot v is going to be a negative 3 times 4, which is a negative 12, plus, 9 times a negative 12. What's that? 12 times 9, 108. Wish I had my calculator. I have a negative 108, and a 6 times a negative 48. 6 times an 8 is a negative 48. So we have a negative 12 plus a negative 108 minus 48. Now, I don't know what that number is, but that's not 0. That's definitely not 0, is it? Definitely not. They're all negatives. Definitely not. In fact, it's a negative 68. 168. So these vectors, since their dot product is not 0, they are not orthogonal. So forget about that. They're not orthogonal. Now, how can I tell if two vectors are parallel? Note, if you have one vector, vector v, and you multiply it by 2, you're getting a vector that's in the same direction but twice the length. If you multiply it by 3, I think all of you would agree that those 3 vectors are all parallel, right? Right? So we could look to see, can we multiply this vector by something to get that one? But before I do that, I'm going to look at vector u. Look at vector u. 3 goes into 3, 9, and 6. So I'm going to factor out a 3. If I do that, that's 3 times the vector minus 1, 3, 2. And look at vector v. What number goes into all those? 4. 1, 4 into negative 12 goes negative 3 and a negative 2. So u is 3 times this vector, and v is 4 times this vector. What do I know about these two vectors? They're opposite of each other, right? They're right? So the one vector is pointing this way, and the other is pointing this way. And this vector is 3 times that, so he's 3 times that. And this vector is 4 times him. These vectors are parallel. They're both parallel. If you can take one vector and multiply it by something to get the other vector, they are parallel. Or if you can show that they're both multiples of the same vector, you can also show that they're parallel. So these definitely are parallel. Now I could have, multiplied negative 3 by what, a negative 4/3 to get that, but I didn't feel like doing the fractions. Okay, let's try another one. Let's see if u and v are perpendicular. So to check orthogonal, I'm going to do dot product. U dot v, which is this vector is 1 comma negative 1 comma 2, and this vector is 2 comma negative 1 comma 1. So if I try dot product, I'm going to get 1 times 2 is 2, negative 1 times negative 1 is 1, 2 times 1 is 2. I'm getting 5. Are they orthogonal? No, because to be perpendicular, they have to have a dot product equal to 0. So they're not perpendicular. Now I'm thinking, parallel. Well, u is 1, negative 1, 2, and v is 2, negative 1, 1. Now remember, vectors are parallel if you can multiply the one vector by something to get the other one. Now if you look, what would I have to multiply 1 by to get 2? 2. But if I multiply 2 by u by 2, I would get 2, negative 2, 4. It's not going to match up. I'm going to get the x coordinate, but I'm not going to get the other ones. So there's no way that I can multiply this vector by some number to get this one. So they're not parallel. Notice, with this one that I did a different way, with this vector, I could have taken vector u and multiplied it by negative 4/3. Because if I multiply negative 4/3 times negative 3, I'm going to get 4. Notice if I take negative 4/3 times 9, I get negative 12. If I take negative 4/3 times 6, 3 goes into 6 2 times, I get negative 8. So I can multiply this vector by some number to get that one. But this one, it just doesn't work. If you take vector u and multiply it by 2, yeah, we'll get the same x coordinates, but the y's and z's. So it's neither. And lastly, let's look at this one. This one, notice they have it, vector u is ABC and vector v is minus BA 0. Let's try the dot product. U dot v is x coordinates multiplied together is minus AB, plus y coordinates together is a times b, and c times 0 is 0. I get a big goose egg, and when two vectors are perpendicular, they are orthogonal. So, when their dot product is 0, they're perpendicular, or your book likes the word orthogonal. And other calc books do too. Okay? All right. Find the direction cosines and the direction angles of the vector. 1, negative 2, negative 1. All right, so remember your direction angles are alpha, beta, and gamma. Alpha is the angle that your vector makes with the x-axis, beta is what it makes with the y-axis, gamma is what it makes with the z-axis. And we proved the following. If vector A is equal to A1, A2, A3, then the cosine of alpha is A1 over the length of A. Cosine of beta is your y coordinate over, or your y component over the length of A. And cosine gamma is A3 over the length of A. Okay, and moving this along, let's figure out what the length of A is. The length of A is, it's vector 1, negative 2, negative 1, so it's square root of 1 squared plus negative 2 squared plus negative 1 squared, which gives me square root of 1 plus 4 plus 1, which is square root of 6. So that's the length of vector A. And vector A was 1, 2, negative 1. So let's see, cosine of alpha is going to be 1 over, we figured out the length of A was root 6. And cosine of beta is the y coordinate 2 over square root of 6. And cosine of gamma is a negative 1 over the square root of 6. And again, I don't have my calculator here, so I can't punch the buttons in, but what if you wanted to find alpha? How would you find alpha? You would do what? If the cosine of alpha is 1/6, the cosine of alpha is 1 over square root of 6. What does alpha equal? The inverse cosine of 1 over square root of 6. Does somebody want to do their calculator right here? Alexis, you got one. Put it in degree mode for me. Put your calculator in degree mode, and then hit inverse cosine, parentheses, 1 divided by square root of 6. 65.9. 65.9? Perfect. Thank you. And cosine of beta, we figured out was 2 over radical 6. So beta would be inverse cosine of 2 over square root of 6. And if you hit inverse cosine on your calculator, again, I want my calculator in degree mode. What did you get? 35.3. 35.3. And we have cosine gamma is negative 1 over square root of 6. And for sure, we want to do this one. Gamma is inverse cosine of negative 1 over square root of 6. 114. Very good. 114 point what? 0.1 degree. Excellent. Notice, if the cosine of the angle is a negative number, your angle is going to be between 90 and 180 because in the second quadrant, cosine is negative. Nice job, thank you. Okay, we did our direction cosines. One more problem and we will call it a day, okay? One other thing I want to go over is in physics, force is F, big D is displacement, and what happens when you take the dot product between a force that's being applied to an object and it gets moved, the object gets moved, represented by this displacement vector. So in other words, suppose I have like a hill here and I have this object that's moving from here to here. That's my displacement vector. But the whole time I'm applying a force in this direction. In physics, F dot D, the force that's being applied, dotted with the displacement vector, how much the object has been moved, is defined to be work in physics. Okay, so this is an example of something that you use the dot product for. Exercise 46 it says find the work done by a force of 20 pounds acting in the direction of north 50 degrees west and moving an object 4 feet due west. So the force, now how do I draw north 50 degrees due west? That means here's my north, here's my east, here's my west, here's my south, okay? And I'm going north, but 50 degrees west of that. So this is 50 degrees. And this is my force, because it's north, but 50 degrees west. North, 50 degrees west of that, all right? And that's a 20-pound force. But the object is moving 4 feet west. And this is 20 pounds. They want me to figure out the work done. So we're going to take F dot D, which is going to be the magnitude of F times the magnitude of D times the cosine of the angle between them. Well, F is going this way, D is going this way. So the angle between them is going to be how many degrees? 40. Okay, and if I write this out, notice F is 20, and if I put the unit in, it's pounds. D is 4, but if I put the unit in, it's feet. And the angle between them we figured out was 40. So if I take 20 times 4 times cosine 40 degrees, make sure your calculator's in degree mode. I already did it out earlier, and I got 21.28. But notice you're taking pounds times feet. In physics, they call that a foot-pound. So it's 61.28 foot-pounds of work. All right, nice job. All right, that's the last problem that we're going to do today. So for your homework, I strongly suggest that you read, and really, as you probably are figuring out, it's much better almost to read the section, look over the section before you watch this video. But if you didn't look at the section, you want to read pages 843 to 848. And then the problems that I strongly urge you to do are 5, 7, 9, 17, 19, 23, 29, 37, and 45. So that's only 1, 2, 3, 4, 5, 6, 7, 8, 9 problems. Piece of cake. All right, I'll see you next time.